Good day. So today I want to continue our discussions in Chapter 9 and look at various ways we can calculate our standard change in free energy. So we have a few ways that we can do this. The first way is to use the equation that we formulated a couple sections ago, where we saw that the change in free energy, standard state for a reaction, is equal to the change in enthalpy at standard state for the reaction minus temperature times the change in entropy under standard state conditions. Now, this is the most general form, or the most general way to calculate it, right? We can do this at any temperature, right? We just plug in the temperature of interest here using, of course, Kelvin temperature to do our calculation. Now, there is another way that we can do this, but it's a little bit more restrictive, right? If we are operating at 25 degrees, we can use standard free energies of formation, or delta G standard states of F. These are very similar in concept to what we saw with standard enthalpies of formation that we can tabulate, and these are in the same appendix in the back of the book. And we can calculate the change in free energy for the reaction under standard conditions at 25 degrees using our now familiar products minus reactant equation that we've used to calculate both delta H of reaction and delta S of reaction previously. Now, this is a bit more restrictive for free energy. So for delta H and delta S, they're not terribly temperature dependent, and that's why we can use them in this equation even though we're operating at different temperatures, right? We're assuming that they have a negligible change over a reasonable temperature range. Now, that's not so true for free energy, so we only want to use this equation at 25 degrees, and at any other temperature, we want to use our delta G equals delta H minus T delta S equation. Now, just a little bit more about these standard free energies of formation. So, this is the change in free energy when 1 mole of compound in its standard state forms from its constituent elements in their standard state. So this is analogous to the delta H's of formation that we saw back in Chapter 7. Right? And so we'll have a list of these in the back of the book, and you can see here from this partial list, right? Sometimes it's positive, sometimes it's negative. We have quite a range. We can see here that the value for any element, right, is going to be 0, right? Because based on the definition, we're calculating the change from itself to itself, right? From the element to the element, so there's going to be no change. You can also sort of see how, just like we saw with entropies and with enthalpies, that there is a standard form, right? And that's carbon, that's graphite, and so it's going to be 0 for graphite, and the other allotrope are going to have some value. So we can find a much more extensive list of these standard molar free energies in the back of the book. And just a note about units, notice the units are kilojoules per mole, just like they are for the delta H's of formation. Now, there is a third way that we can calculate delta G, and that is using Hess's law, another concept that we saw back in Chapter 7, where if a reaction can be expressed as a series of reactions, then the sum of the delta G values for those individual reactions can give us the delta G of the overall reaction. So we did this back in Chapter 7 for delta H values, so for enthalpy values, where we took 2 or 3 equations and we had to rearrange them to add up to an overall equation and then we could sum up the corresponding delta H values. And we can do something very similar for delta G's. Now, this is possible because just like enthalpy change, free energy change is a state function, right? We're only interested in the beginning of the end, not the exact pathway that we get there. So, a couple of things to keep in mind as we're manipulating these reactions to get them to the way we need them in order to add up to our overall reaction. We have to keep in mind a couple different things. First of all, if we need to reverse the reaction, then the sign of delta G will be reversed, just like it was when we did it for delta H. And if we have to multiply the coefficients or change the coefficients in some way, say doubling them or cutting them in half, etc., then delta G will be changed by the same factor. So if we double all the coefficients in our reaction to make it work, then we have to double delta G, etc. So again, delta G of reaction is extensive, right? It's going to be bigger if we react 2 moles versus if we react 1 mole. Right? So these are 3 different ways that we can get to this delta G of reaction under standard conditions, right? We can use our delta G equals delta H minus T delta S, or we can use our values in the back of the book and calculate it using products minus reactant using our delta G's of formation that we can find in the back of the book. Now again, remember that can only be done at 25 degrees, whereas this equation here can be used at any temperature. And I would recommend using this obviously at any other temperature other than 25 degrees. And then I would recommend using the values in the back of the book if we're operating at 298, right? It's a simpler calculation, and you don't need to know delta H and delta S. So oftentimes in problems, they won't give you that information. They will just expect you to know that at 298, you can use the values in the back of the book. At this point, I want to talk a little bit more about delta G in a little bit more theoretical way and address the idea of why free energy is free. What do we mean, really, when we talk about this free energy? So, free energy we can define as the maximum amount of energy available, in other words, free, to do work if delta G is negative, right? So if delta G is negative means, we're going down in free energy, so free energy is being released over the course of reaction. Now, what we see is that for many reactions, the change in free energy is less than the change in enthalpy, right? Our delta H of reaction. Well, and the question is, what does that mean? Well, the difference between these two values, right, is the amount that is not available, right? So the free energy represents what is available to actually be used for do work, and there is sometimes a difference between what is actually available and the total change in enthalpy for the reaction. And so we can look at, for example, the reaction of carbon plus hydrogen to give methane here, right? And we see that it has a delta H of minus 74.6 kilojoules, but a delta G, right? So this is my delta G here of 50.5 kilojoules, or minus 50.5 kilojoules, right? That's how much is available to do work. So, for an exothermic reaction like this, and we see this for many exothermic reactions, some of the heat that's released due to the enthalpy change goes into increasing the entropy of surroundings so it's not available to do work. So remember, in some of these exothermic processes, this is really important, right? Because they actually have a negative delta S. Right? And so remember, if you have a negative delta S of reaction, then in order for that reaction to be spontaneous, the delta S of the surroundings, so this would be our system, so the delta S of the surroundings must be positive and more than this, right? So in this case, it would have to be the entropy of the surroundings would have to go up by more than 80 joules, or more than 80.8 joules, in order to make delta S of the universe positive, right? Which is, a criterion of the second law of when a reaction can be spontaneous. So what we see is that often some of this enthalpy change is being used as heat to heat up the surroundings so it's not available to do work, or, what we might consider other work. And even if the reaction isn't exothermic, right? Even if the entropy isn't negative, right? So it doesn't necessarily have to go to heating up the surroundings. We often will see energy lost to the surroundings as heat during the course of the reaction. So the actual amount available is less than the overall enthalpy change. So as we just mentioned, right, the delta G of reaction is the maximum energy available to do work. Now, even for reactions that don't need to heat up the surroundings, right, this represents a theoretical limit, right, and is typically not going to be the actual free energy change that we see, right? This would be true if we had a truly reversible reaction, which we saw in section 4 a little bit earlier, where, based on at very specific conditions, if for an infinitesimal change, we see a reverse in the reaction. And so under most conditions, this is not true. And so typically we don't ever see this theoretical limit. But in real reactions, right, what we see is that some, if not most, of the free energy that would be available is lost as heat, right? So this is what we think about as just the heat being given off as, we lose reaction, right? So, for example, when we charge a battery, right, we lose heat to the wires, right, through the wires as the current flows, right? This is lost free energy, right? That energy is not available to operate the motor, right? Or to recharge the battery if we're thinking about that way, right? And so if, for example, when we recharge a battery, we always have to put in more energy than what's actually necessary to recharge the battery to account for this, right? So the bottom line is that this delta G represents a theoretical limit, and in most reactions, we lose some, if not most, of this free energy to non-useful work, to heat along the way. And real reactions are irreversible, right? They're not this very sort of restricted theoretical type of of ideal reversible reactions. Now, all of these examples that I'm saying, presuming, of course, that delta G is negative, right? Because that way we're giving off free energy, right? But what if the delta G is positive? What do we have, a non-spontaneous reaction? Well, then the delta G, the change in delta G, represents the minimum energy required to make a non-spontaneous reaction occur. So as I mentioned earlier, an example of this would be, battery recharge. So the spontaneous direction, right, is battery discharge, right? So you use your battery for whatever, right? That's spontaneous. If we want to recharge it, we want to force it to go backwards, then we have to put in energy, right? We plug it into the wall. And so the minimum amount of energy required to do this, it would be our positive delta G for that non-spontaneous reaction, right? That's the minimum that we need to put in to make this non-spontaneous reaction occur. All right, so that sort of concludes this little theoretical talk about delta G. So we're going to do a practice problem here, a couple practice problems looking at calculating delta G here in just a second. And in the last couple lectures for this chapter, we're going to talk about some other aspects of free energy, and that being non-standard conditions, right, which we talked about with enthalpy back in chapter 7, and we'll look at the connection between equilibrium and free energy. So now I want to do a couple of practice problems calculating delta G. So in this first problem, you can see it says calculate the delta G of reaction at standard state at 25 degrees Celsius using standard free energies of formation, right? So it tells us here, that we're going to use this data in the back of the book, but as a reminder, right, we can do that because of the fact that we're at 25 degrees, right? So to remind ourselves, that equation is delta G of reaction at standard state equals the sum of the coefficients of the products minus the delta G's of formation of the products minus the sum of the coefficients times the delta G of formation of the reactants. So if we look over here, I have the values that you would find in the back of the book for all the species in our equation. And if we go ahead and plug it in, I'm going to do the products and reactants separately here and then just subtract them. So let's do the products first. So we only have one product, and that's going to be the C2H6, and that has a value of minus 32.0 kilojoules per mole. Now, we have a coefficient of 1, so that's all we need to worry about. Now, for the reactants, we're going to sum together our reactants, C2H4 and H2. So we have one C2H4 at 68.4 kilojoules per mole. And 1 mole of H2 being an element, it has a value of 0 kilojoules per mole. And so our total here is 68.4 kilojoules per mole. And so now if we do our products minus reactants, it's going to give us our delta G of reaction. It's going to equal our minus 32.0 kilojoules per mole minus the reactants at 68.4 kilojoules per mole to give us an overall value of minus 100.0 0.4 kilojoules per mole for my delta G of reaction under standard state conditions. So, the other thing that this question didn't specifically ask us, but what we're often asked is to address whether this reaction would be spontaneous under these conditions. And so since we have a negative delta G of reaction, we then would say that under these conditions that this reaction would indeed be spontaneous. Okay, for our next problem, we're going to calculate the delta G of reaction standard state, but now we're going to do it at 50 degrees Celsius and decide if this reaction is still spontaneous at 50 degrees. So we're working with the same reaction that we did, but remember this time, because we are at 50 degrees or not at 25 degrees, we're going to have to use our delta G equals delta H minus T delta S equation. Now, depending on the problem, sometimes they'll give you the delta H of reaction and the delta S of reaction, right? Other times they'll not, and maybe they'll give you data from the back of the book or expect you to look up the data in the back of the book, depending on, if it's a homework problem or a problem on, say, a problem set or an exam. But in this case, we have the data from the back of the book. This is what you'd find if you looked up the enthalpies of formation and the standard molar entropies. Oops, don't want that there. Sorry, that's not a change. That is just an S. So we first need to calculate the delta H and the delta S of reaction. Now, we're going to use our products minus reactants equations. So we're going to use delta H of reaction equals delta H formation of the products minus the sum coefficient times delta H of formation of the reactants. So, if we look at our products, our product is the C2H6, so we have minus 84.7 kilojoules per mole minus our reactants, which are going to be positive 52.4 kilojoules per mole plus 0 kilojoules per mole. Now notice all of these have a coefficient of 1, so we don't have to multiply by any of these things, but if we did have coefficients, we would have to multiply them by all of these. So if we do our math, our delta H of reaction here ends up giving me a value of minus 137.1. So we got minus 137.1 kilojoules per mole for our delta H of reaction. Now, we're going to do the same thing for delta S. We're going to calculate our delta S of reaction, again, using the same kind of problem as we did here. We do our products minus reactants, so instead of writing out that equation, I'm just going to plug in my values here. So if I look at my entropies for my product, I have 229.2 joules per mole Kelvin minus my reactants, which are 219.3 joules per mole Kelvin plus 130.7 joules per mole Kelvin. Oops. So if we sum all that together, we're going to get an overall value of minus 120.8 joules per mole Kelvin. Equals my delta S of reaction. So now I have a value for my delta H of reaction and my delta S of reaction. So now I can go ahead and plug it into my overall equation for delta G, and we can get the delta G of reaction equals my delta H, or minus 137.1 kilojoules per mole, minus the temperature. So our temperature is 50, so we have to convert that to Kelvin. So that's going to be 323.15 Kelvin times my change in entropy. Now, one thing we always have to keep in mind is notice that my entropy values are in joules. So regardless of how I do it, both of the delta H and the delta S have to be in the same units. So since I already used this in kilojoules, I'm going to go ahead and convert this to kilojoules. And so that's going to equal a negative 0.1208 kilojoules per mole Kelvin. So I'll go ahead and use that here. 1208 kilojoules per mole Kelvin. So if I go ahead and take my delta H minus my T delta S value, I'm going to get my delta G of reaction is going to equal a negative 98.1 kilojoules per mole. Now, again, we can address the question of spontaneity, and the key comes down to our sign of our free energy. And since we have a negative change in free energy at 50 degrees, this reaction is indeed spontaneous. Now, it's a pretty typical equation, but one of the things I want to show you now is something I mentioned earlier, is that what if we wanted to, for this reaction, predict when this reaction would become non-spontaneous, right? So at what temperature would this become non-spontaneous? Well, we can do that. Let me just switch to a clean piece of paper here. And so we can take our delta G value, remind ourselves that it was minus 98.1 kilojoules per mole at 50. So what we're going to do is we're going to try to find at what temperature does the reaction, in this case, become non-spontaneous, because it's already spontaneous here. So the technique that we use is we want to find where delta G flips from being negative to positive. And so we're going to set our delta G value equal to 0 equals delta H minus T delta S. So we're simply going to solve for T where delta G equals 0, right? Where that's going to change from positive to negative. So we plug in our same delta H and delta S values that we use. So our delta H value is negative 137.1 kilojoules per mole minus T times my delta S value, which was negative 0.1205 kilojoules per mole Kelvin. And so now, if we solve over our math, we get T if we rearrange and solve for T, we get T equals 137.1 kilojoules per mole divided by 0.1205 kilojoules per mole Kelvin. Of course, my kilojoules per mole cancel out, and my units here are going to end up in Kelvin. So if I do this, we get that T equals 1,141 approximately degrees Kelvin, or Kelvin, and that's where our reaction would become non-spontaneous. Right? So just to be clear, oops, sorry, let me check my math here. I had a little error here. Not much, but wanted to double check that. It should be 1,138 Kelvin is where this reaction would become spontaneous. So let's think about this for a second. So remember that this reaction had a negative delta H and a negative delta S. So if we remember back to our sort of chart that allowed us to sort of estimate what conditions the spontaneity would be, if they are both negative, right, what does that tell me about the conditions of spontaneity? Well, it tells me that the enthalpy, right, is in my favor, right? It's exothermic, but we have a decrease in entropy, right? So in other words, we want this reaction to become spontaneous, right? It's going to become spontaneous as it reaches this higher temperature, right? And at any temperature above this, it's going to become spontaneous or non-spontaneous. So this reaction, again, sorry, I just repeat myself here. This reaction becomes spontaneous, or not, excuse me, non-spontaneous as we move to higher and higher temperatures, right? So it was spontaneous. If we look back at our numbers, right, it was spontaneous at 25 degrees with a value of minus 100.4 kilojoules. As we go up in temperature to 50, right, it becomes less spontaneous, right, minus 98. So what we can see here is as we're raising the temperature, it's becoming less spontaneous, and eventually at temperatures, in this case, very high temperature at 1138, the reaction will shift to be having a positive delta G and become non-spontaneous, as we would expect for a reaction that has a negative delta H and a negative delta S, which tend to become spontaneous at low temperatures, non-spontaneous at higher temperatures. Now remember, anytime we talk about those, the temperatures are all relative, right? In this case, 1,000 degrees is not high enough temperature, right? You have to get up even higher. So we can't think about low and high in sort of our standard notions of what we think about. It's all going to depend on the reaction. So this is just a technique that allows us to, when that change occurs. So in this case, since we knew it was going to be we knew it was spontaneous, we were looking at when it flips to being spontaneous or non-spontaneous. So we can use this as sort of our guide to know that it was going to become spontaneous eventually at some higher temperature, and spontaneous as we go to below this temperature. So this is our benchmark. We go above this, non-spontaneous, below this, spontaneous, because both of these are negative.